So good morning, everybody. Thanks for joining the session. This is actually the last session of the year, 2021. And I thought we should have a couple of guests today. So I think it's a real privilege to have Thomas and Jessica who are gonna give the presentations today. But just before we start, I wanna thank you, all of you, and particularly all the speakers who presented their work this year. You see them on the slides. So I want to thank Kilian, Chris. Thanks so much, Julie, Ludovica, Bruno, Mariana, Aurélien, Gaël. And next year we'll have Valérie and Davides. Thanks so much, guys. You made this journal club a real success, I guess. And please do not hesitate to check the website, the Lyric Education website, where you can watch all the recordings from the previous session. So please have a look there and register as well. All right. As I said, it's just amazing to have you guys to this meeting. But just before I introduce you, let me actually introduce you to the team, to the people who are connected today. We have actually a couple of teams on Zoom, mostly from the CHUV in Lausanne. The team is headed by Matthias Stuber, that you all know. Matthias, you might be around, right? We have people from the imaging team of Lyric. The team is led by Bruno Caisson. We also have a couple of clinicians, usually from the Hospital of Bordeaux. The team there is led by Hubert Cochet. And we also have AI experts that are calling from INRIA, the team of Maxime Sermezan. So Thomas, it's just a pleasure to have you today. You're calling in from Germany, right? From Tübingen. Thomas is working at the University Hospital of Tübingen. He's actually leading the MIDAS team, the Medical Image and Data Analysis team. So a little bit of background on Thomas. He has spent, 3 or 4 years at King's College London, correct me if I'm wrong, Thomas, during his postdoc. And he's also spent a couple of months in China during his master degree. So today, Thomas, you are gonna share your insights about fat saturation in cardiac MRI. But everybody, just so you know, this is just one topic among many others where he is a real expert. So Thomas has also a strong expertise in medical imaging in general, in AI, in data acquisition, and in data reconstruction. So please, if you have questions other than fat saturation, please do not hesitate to ask him the questions, to challenge him, and I bet he will have the correct answer to your question. So Thomas, it's a privilege to have you today with us. The Zoom floor is yours. We're gonna stay quiet and we are gonna enjoy your presentation. Thanks.
Thanks a lot, Aurélien. Thanks for a very nice introduction. And yeah, also welcome from my side. So I have the pleasure today to talk to you about FIS. So let me quickly share my slides here. So as Aurélien already introduced, this was work I did during my postdoc time in London at KCL. So I also want to do a big shout out to all the colleagues I had there who contributed to this work, also namely Aurélien, who contributed a lot to this work. So today, there will be cardiac applications, but as a short disclaimer, there will be also non-cardiac applications because I want to talk a little bit more in general about the 3D Cartesian FIS imaging and how we accomplish that. So as a motivation, it is obviously for cardiac imaging, and there we need to deal, as you all know, with respiratory and cardiac motion, which you can deal by handling them retrospectively, for example, and continuously acquiring data in the free-running acquisition styles. But furthermore, what we also observed is that fat can be a major image quality degradation factor which lets us then, or lets other groups also as well, to come up with ideas on how could you provide a fat suppression or separation techniques by either interleaving spectral selective pulses, phase sensitive fat suppression, or performing Dixon imaging, for example. And in this work, we also wanted to deal with how can we provide an adequate fat suppression for a balanced SFP sequence, where we could also be able to depict the coronary arteries and are not impaired by epicardial fat, or also fat arising from a subcutaneous fat arising from the chest wall, which could then also introduce artifacts due to the respiratory motion. So that's where we looked at the FIS technique, which was proposed by Kotzoglu and Edelman, the fast interrupted steady state. And the idea is that you modulate the BSSFP sequence, and by modulating, we mean interrupting the steady state of the alpha pulses, RF pulses over time. So if you look, what does this bring us? We look here on the left-hand side, we have a standard BSSFP sequence. We see the frequency response pattern. We have the pass band here and the stop band around here. And for 1.5T scanner, we have our fat signal at around 3.5 ppm, so around 220 hertz. So we see for a BSFP, we are again in the passband area, so we are capturing this signal. However, for FIS, on the right-hand side, you see we could get the signal down. We can have a broader stop band, and we can even nearly suppress the whole signal, and that's the idea behind it. And this was shown for 2D radial acquisitions. So we looked into it, how we could extend this for the 3D Cartesian case, since we are working with 3D Cartesian samplings. So again, to show you how this sequence then looks like, we have a ramp up pulse, then a series of pre-dummy pulses, and then we have the so-called FIS modules. And I've zoomed in here in one for you. So we have always this interruption happening with this alpha over 2 down and alpha over 2 up pulse. And we have then followed again in this FIS module our normal BSFP train, where we have the alpha pulses and intermittent readouts. And then after a certain time, we ramp down again by alpha over 2. We do again the interruption, and then the next FIS module starts. So as a key ingredient, what we have observed and what we will see in the next few slides is that we need the pre-dummy pulses. We also need to address spoiling problems to combat residual transverse magnetizations. And we also need to look at, most importantly, the interruption rate. As I said, one FIS module is comprised of several readouts with of the BSSFP train. So you can decide how often do you want to do this ramp up and ramp down. Obviously, the more you ramp up and ramp down, this costs you scan time. But we will also see that it will have a major impact on the observed pass and stop band behavior, and then ultimately on our observed image quality. And that's what I want to show you in the next few slides. So let's first start off, why do we need the pre-dummy pulses? Obviously, we are by doing this interruption always kind of like in a quasi-transient state of imaging. We are no longer in the steady state of the BSSFP sequence. However, to still get satisfactory results and to still be in a quasi-steady state, we want to look at how does this affect if we apply these pre-dummy pulses or not. So here we have the temporal on-resonant behavior of our signal. So it's just the water signal, where we see for different compartments, the EPG simulations, how they are reaching the steady state. And after a certain number of readouts, we see in the spectral response, if we are imaging too early, we still might get some very high peaks here at around our desired frequency, which can cause an artifact. But if we are doing this later in time, we have reached a steady state, let's say, for the fifth sequence as well. So that's why we have reached this quasi steady state. Now, if we look at the off-resonant signals, which are of more interest to us, especially the FET signal shown here in blue, for this off-resonant frequency, over time we see a very fast decay of these off-resonant signals. And so we can assume that applying a certain dummy pulses allows us to acquire the fizz in a quasi-steady state. The next ingredient, as already said, is we need to apply spoiling, and two types of spoiling, gradient spoiling and an RF phase cycling. And if we do so, we get out the spectrum as shown here. So what happens if we don't do either one of them? If we omit the RF phase cycling, we get a broadened passband around the zero DC or around the Hörder signal, and potentially then already an incline again in the other signals. And this gets even worse if we don't do any gradient spoiling between the different fizz modules. We see a spectrum which gets again closer to the BSFP, but then modulated down again due to the interruption rate of the fizz alpha or the alpha over 2 signals. So it's quite simple. What you do, you just apply a phase spoiler, phase encoding, and spoilers and RF phase cycling between the different fizz modules. And we've just chosen an RF phase cycling with a golden angle starting point, but this is arbitrary. You can also use any other value, but with this we were certain that we did not repeat repetitive RF phases over time again. So spoiling is really needed, that you get the desired frequency spectrum and that you can then suppress any residual transfer magnetization from one fizz module to the next, which could really introduce severe artifacts. And as the last ingredient, as already said, we need to look at the interruption rate. We can call this either the interruption rate, how often, so 1 divided by TRF, how often do we interrupt, or how long is our duration of the fizz module, or we could also express this in terms of how many readouts do we have within our fizz modules, and this is what we usually call N. So when we have a fizz module of N equal 2, we have 2 BSFP readouts within the fizz module. And what we see here for a fixed flip angle, we see here the total frequency response pattern now in color coded. So again, we see here the precession frequencies, but now on the y-axis, we see the different interruption rates. And blue is small, sorry, I forgot the color coding here. And we see that for certain amounts, if we go very, very low on our interruption rate, so meaning very, very long fizz modules, so a lot of BSFP readouts per fizz module, we see that we get, again, through several parts where we see increased signals again. But there are also valleys within there which would allow us to operate within this regime. And furthermore, this also depends a little bit, but not so severely, on the flip angle. So if we now take one specific interruption rate, which corresponds here to a readout of 2 BSFP readouts, then we see that the flip angle does not have a too severe impact. Obviously, if we are imaging too low, we also don't get any signal in our passband around the water. But as soon as we hit our certain threshold, we could say we nearly stay the same in terms of like passband, stopband behavior. So that's at least good news. So we don't need to optimize about the flip angle, but we need to take care about the interruption rate. So how could this now be integrated into a free running acquisition? And usually there are different flavors what you can do, and what we have also then investigated. And I think Jessica will be talking a little bit more about the interruption water selective, but I'm looking forward to her talk. I want to show you now results on what we have achieved for the FIS sequence here with this interruption rate, and with the water selective excitation, which we have done as a comparison. So the acquisition, as already said, we need to deal with respiratory and cardiac motion. So we have the data acquired with the 3D Cartesian variable density Caspar sampling, and with an embedded self-navigation signal, which gives us then out the respiratory and cardiac motion traces, which we can then use for first performing respiratory only binning, ignoring the cardiac phases. That gives us, allows us to reconstruct an initial image on which we can then perform translational respiratory motion estimation. And this translational respiratory motion estimation, we embed then into respiratory corrected and cardiac binning, together with a cardiac soft weighting along the different cardiac phases according to Gaussian soft weights, as shown here on the top. And this then gets all sent into reconstruction, which is multi-bin Prost reconstruction. So just to explain this shortly, we have a certain search region shown here in yellow. We pick out one desired reference patch, and we look in all the other bins, which are here our cardiac phases, for similar patches, and we stack them along a large tensor. We then perform, get this self-similarity matrix and perform a singular value decomposition to get our noise-free components, which we back aggregate into the images. And then we iterate over by applying also data consistency, and by that iteratively get out our denoised and cardiac motion resolved image. So as already said in the disclaimer, not only did we look at cardiac imaging, but also looked at some phantom imaging first, and also upper thigh imaging and some breast hold abdominal imaging. We've scanned several different subjects, and primarily with the interest of examining the impact on if we change imaging resolution in different ranges, which will then affect obviously how long our readouts are and how long then our TETR, and respectively then the duration, the TRF of our FIS module is. And by that, how in this range, how can we then change the FIS module length? So have we one readout per FIS module? So we always do the alpha over 2 down and up after one readout, or do we have 2 readouts per FIS module, and so on? And furthermore, we also then examined the impact of the bandwidth, and also then how does this then relate to different acquisition times. And here, as you can already see, the more readouts we have, the closer we get to a normal BSFP acquisition range. But the more often we interrupt, this costs us really severely in scan time. So now let's look at some results, and this is quite a busy slide, but let me step you through it. So on the left-hand side, you see the conventional BSSFP imaging here in the upper thigh. And on the other columns, you see the respective FIS imaging with a readout module of N1, 2, and 4. And you always see the image and the respective spectral response to it. And the dashed line always shows you where the fat signal should lie. So you could already appreciate that we are able to do a very nice fat suppression with the FIS imaging, allowing you some angiography imaging of the upper thigh. But what you could also see is that depending on the interruption rate, the other passband spectrum always moves a little bit closer to our fat spectrum signal. And you can see this very clearly here for n equal to 4. We have already moved this very close or in, so that we can see we get a very strong artifact behavior in this case. And this is not only depending on the interruption rate, but as already said, this couples together with the imaging resolution. So if we have a low resolution, we have a wider range of where we can control this. The higher we go with resolution, the tighter it gets. We can also then look at another example where we can just also rotate and see that this holds, this fat suppression holds very homogeneously in all 3D dimensions. As I show you here, we have an axial map and a coronal map and assumed inversions where we can see that we get very nice fat suppression for this two examined subjects here with a FIS n equal to 1, however, at the cost of scan time. We can also move this to abdominal imaging, and we see the same effects then there again. A very nice fat suppression if we do the FIS imaging. However, already at FIS n equal 2 and FIS n equal 4, we see severe impact of artifacts and residual and aliasing of the content, which then obviously is no longer a desirable image. So here we may have different fat compartments. So it's not only most like a fat signal 220, but we have a wider range of fat signals throughout this range here in the abdominal case. So we will most likely be impaired here by various different fat compartments. And as a last example, I want to show you here our results on the free running image, where you see top row the BSSFP for subject with high epicardial fat content. In the middle row, you see water selective BSSFP sequence, and on the bottom row, you see the FIS imaging now with an interruption rate of n equal to 2 in order to make a compromise between scan time and still sufficient fat suppression, but without being impaired by these artifacts. Also, I want to note that in order to bring it to a similar scan time, the FIS was twice as fast accelerated as the BSSFP sequence. And here again, you see different subjects and results now more time resolved for the BSSFP. Water selective and FIS. However, for these subjects, we did not see too much of an impairment of fat-related content. However, you can appreciate still the fat suppression capabilities, especially in subject G, for the water selective and the FIS, with both of them, I would say, powering out. However, with the clear advantage of the water selective in terms of scan time, since this we can perform in around 2 minutes, where the FIS imaging would be performed in around 5 minutes. So this brings me to my conclusion. We have seen some limitations of this work, primarily the increased scan time due to the interruption and the required gradient spoiling, which costs you always a few nanoseconds between the modules. We have seen this dependency of the fat suppression on the interruption rate, or how many readouts you have per FIS module, which is also a parameter you rather want to set fixed for all the imaging scenarios. But we have seen that this really depends on if you're doing upper thigh imaging or if you're doing abdominal or cardiac imaging. There are different ranges of interruption rates which you could apply depending on the fat compartments you're trying to suppress. And so a more thorough comparison to other fat suppressions is needed. And but our takeaway, what we have seen here, is that the water selective, especially in the cardiac case, was doing a pretty decent job for us. Nevertheless, we could show that we offer a feasible and homogeneous intrinsic fat suppression. We don't need to interrupt with some spectral selective fat suppression pulses. This smoothly integrates into the BSSP acquisition train. We could show that we are still imaging within a quasi-steady state. And so we get very nice signal behavior and no artifacts related to that. And this also holds for different types of applications, which we have examined here. So with this, I would like to thank you very much for your attention. And I would like to thank again all the colleagues from London, as shown here on the picture on the right, who primarily contributed to this work. Thanks.
Thank you very much, Thomas. That was impressive, as always. I think your connection was a little bit unstable at some point, but we all managed to nicely follow your talks. Do we have any questions from the audience? Please raise your hands. Yes, I can see you, Matthias. Go for it.
Hi, Thomas. Thank you very much for this great presentation and for sharing your results with us. I think you did a very thorough job in looking at this parameter space and to figure out where it succeeds and where it fails. And unfortunately, also there in FIS, there is no magic, right? So if you want to have a better suppression, you have to invest more scanning time. But I have 3 questions for you. The first one, if you show your slide number 7 with the green surface area, green and blue, I think blue was better than green. There are quite some discontinuities on that graph. And I was wondering where these discontinuities are coming from.
Yes, so this seems to be discontinuous, and but the y-axis was also discontinuous.
Exactly. So this rarely happens, right? Yeah. So always, if we see something like that, this says, "Oh, that might be an opportunity." So where is that coming from? Is this perhaps your simulations that have a certain granularity, or is that something intrinsic to FIS?
I doubt that it's something intrinsic to FIS. I guess it's more related to the EPG simulations, which we have conducted there. Would need to take a further deep dive into the simulations here, but I agree with you. It could be a valley to explore, but we have so we tried these different interruption rates. I haven't shown them here. But at the end, it was not worth to go for a larger FIS or number of N. for readouts per FIS module, as this did not reduce much of the artifacts as we would hope for.
Okay, great, thank you. The second question is on your CINIs. This may have been hard to appreciate on this screen, I'm not exactly sure, but it looked to me as if there was like some kind of a black rim artifact that all of a sudden pops up and then goes away again. Is that only a projection on the screen, or have you really observed that?
I haven't observed that, so that might be just a connection or visualization problem. I haven't seen that.
Okay, so you didn't see these black circles on the myocardium in your CINIs?
No, this is probably just a scaling effect of probably the GIF I've created.
It's a transfer function of Zoom and GIF, or I don't know. Yeah. Okay, and then my last question is, do you continue now with that? Where do you take this?
Sorry, can you repeat that again?
Do you continue with that? Where do you take this now?
Yeah, thanks. So my takeaway is that FIS is very interesting, but in terms of scan time that it costs you, we have already seen like the publication which followed after that was the free running acquisition, and there we switched into the water selective excitation pulses, which proved to be the easier or the better choice in terms then of reduced scan time and still satisfactory fat suppression. So FIS is a very good application and it has its merits, but I don't know if it's the right choice for 3D Cartesian free running acquisitions.
Great, thank you.
Can I say something quickly?
Yes, go for it, Jess.
We can discuss afterwards, but I think it's so interesting because I never did in vivo scans with NS1 and NS2 because it was too long, and we didn't have these artifacts with NS4 and NS8. But I'll show you later because it's also some, but then you see other artifacts, you know, so.
Exactly. I think that's quite particular where we see this very much pronounced for the Cartesian case. I also then talked with Jonas and Bob Edelman about this, and they also didn't observe it in their radial acquisition. So I guess this is quite severely where we can see this easily popping up in the Cartesian cases, and maybe this is then a little bit more smeared out to the radial acquisitions. Yeah,
I think so too, but you know, it's still very novel, so it's interesting to explore.
Exactly. Yeah.
Thomas, have you looked at the impact of the RF spoiling increments, which was set to 100 or 110 in your case? Have you looked at, you know, changing this parameter, and what was the impact on the final image quality?
So the impact was primarily if you do it or if you don't. The number or the starting increment we have chosen with the golden angle was primarily that we don't repeat the same RFA cycling too often and again. And we also looked then at different ways on how we could cycle this through. So, and there have already been previous studies like 20 years ago where RFA cycling was invented, and people looked at if you do a linear increment or quadratic increments and so on. And this incrementing structure proves to be the most robust and the less repeating in this regard. And since we're looking at very long acquisitions, we opted then for this incrementing strategy.
Okay. Do we have any other questions from Lausanne or from Bordeaux? No one. All right. Let's move on to the next speaker. Thanks so much, Thomas. Maybe still around. We'll have maybe more discussion at the very end of the session. Jess, welcome. If you could please share your screen, amazing. So just a very quick introduction. Most of you actually know Jessica. She's been working at CHUV in Lausanne for a couple of years now. And you're actually still very much involved with the team in CHUV as you are supervising Adele. Jess, you've been awarded the quite prestigious Ambizione Carré grant, and more recently the Excellenza grant from the SNF.
That's right.
And since a couple of weeks, you are now assistant professor at the Faculty of Medicine in Bern. So you're also going to highlight us on fat saturation, and the title of your presentation is, as we can see there, MRI on a diet, challenges and approaches for fat-free MRI. Jess, we're very much looking forward to listening to your talk. Thanks.
Yes, thank you for having me. It's really a pleasure to talk a bit about science again. I've been doing a lot for admin recently. So my talk will be about MRI on the diet, challenges and approaches for fat-free MRI. Since Thomas was there and presented a lot about FIS, my FIS part is going to be a bit reduced, but I replaced it with some water excitation pulse talk. So as you know, fat suppression is important. If you don't suppress it, it might hinder the visualization of small anatomical structures. And also if you want to quantify fat or quantify water better or quantitative mapping or anything like that, it's really beneficial to be able to do some type of fat resolved imaging, especially if you have multiple tissue components in the same voxel. So there's a few approaches for fat resolved MRI. One is those methods that focus on the suppression of the fat signal. So you can think of adiabatic inversion pulses like SPARE or the very conventional fat saturation pulse CHESS. You can also think of water excitation pulses, but those are typically characterized by rather lengthy RF pulse durations. And there's also methods that rely on water-fat separation, but they're typically lower in SNR because they use gradient echo sequences. So all these methods have their disadvantages and advantages. And I would say that if you want to work on free running approaches or techniques that are radial, then a conventional fat suppression might not be the best choice, because when you use radial trajectories or K-space readouts, then it means that your signal weighting is dominated by the K-space center. So in this example, I'm showing just a regular acquisition. One is Cartesian, one is radial, with a very standard fat suppression pulse before that. And you can see that in this middle compartment, fat is very well suppressed with the Cartesian trajectory, but if you go to a radial trajectory, fat signal is not suppressed. And this is because fat has a very short T1, so fat signal recovers quickly, and because your signal weighting is dominated by the K-space center, in your imaging data, you still have a lot of residual fat signal. However, conventional water excitation pulses are rather lengthy. So I spent quite some time, like I would say since 2015, on trying to optimize water excitation pulses and kind of trying to design some new approaches. And one of them is Libre. And I will first go to why is a conventional water excitation so long. And this is because if you consider a binomial water excitation 180 pulse, what happens is that you apply an RF excitation pulse, then the magnetization rotates, and then you're waiting for fat and water to dephase by 180 degrees. And then you apply a second RF pulse. So this type of method relies on the dephasing of water and fat, which of course makes the pulses very lengthy when you go to lower field strengths. And at around 3 Tesla, this pulse duration is at least 1.1 millisecond, because this is the time that's required for water and fat to dephase by 180 degrees. So then I was thinking, okay, can we maybe optimize this? Can we speed this up? And the kind of intuitive approach of Libre is as follows. If you take a rectangular pulse in time domain, if you take the Fourier transform of that, you get the sync-shaped pulse in frequency domain. If you make this type of pulse longer, that means that your frequency response becomes shorter. You can already see if the dotted line is representative of your fat frequency, that you are already closer to the zero crossing of your sync function. So then a simple idea was, what if you just apply an off-resonance frequency modulation on this first RF pulse? We can keep a short pulse. The frequency response is still long, but it's shifted. So the zero crossing of the sync pulse corresponds to the fat frequency. Of course, this is a very simplified view of how Libre works, because it doesn't work with one pulse. What happens is that to have a better fat suppression, you kind of do a second pulse with phase modulation. And this makes a very nice increase in the fat suppression bandwidth. As you can see here with the Libre pulse, you have a fat suppression bandwidth of about 300 Hertz compared to the conventional 1-1 binomial excitation, which is about 50 Hertz. So the cool thing about Libre is that because you're modulating this pulse in terms of frequency offset and phase, you can shorten the pulse duration by increasing the off-resonance excitation frequency. And we've even done studies at 3 Tesla where we successfully reduced the pulse duration to 400 microseconds. And just to put things in perspective, a normal excitation pulse in the standard sequence of Siemens is about 300 microseconds. So we had effective fat suppression with a 400 microsecond pulse. This particular result is not published though. So in vivo, if you compare these different fat suppression methods, we observe that in general, the fat SNR is significantly lower. So we suppress the fat better, but we also have a broader fat suppression band. So if you compare again a conventional water excitation pulse with Libre, you have overall a better fat signal suppression, as you can see here, because the signal is just darker. But you also have in regions closer to air tissue interfaces where you typically have more of resonance signals. You have it is suppressed with Libre. So we explored several applications. One is in the field of high resolution cartilage T2 mapping, because this type of application is typically hindered by chemical shift artifacts because you have very high resolution. So if you don't have enough receiver bandwidth, then typically your fat signal is falling over in your cartilage tissue because bone marrow contains a lot of fat, and then you get this type of chemical shift artifacts. So here Libre really helped characterizing cartilage, improve the quantification of the tissue, but also the anatomical visualization. Another application is that of real-time eye motion imaging, where the focus is really on imaging the optic nerve and how it moves. And you don't see it here because the tissue is very well suppressed, but this optic nerve that you can see here with this little line is really surrounded by fat. Plus, you have the sinuses and the air cavities in the nose. So this method really benefits from very well suppression of fat, but also with a very good bandwidth. Another application is that of coronary angiography. In this particular study, we ran this in heart transplant recipients at 3 Tesla, where patients received gadolinium slow infusion. And here on the right side, we have a volunteer study conducted at 3 Tesla, where we again observed that Libre suppresses fat in a better way than conventional water excitation. However, there are, of course, disadvantages with Libre. One is that the main one is that although you can make your RF pulses much shorter, if you make them shorter, you increase the RF excitation frequency, which increases the RF power. And if you change the magnetic field strength, this would even be more of a problem. If you would decrease the field strength, this behavior becomes worse. So Libre I would say, is very beneficial at high field, would not work as well at low field. And if you, as you can see with this graph, and also this RF power is kind of detrimental, because just if you look at this graph where we see the total pulse duration, I mean, I told you you can decrease the pulse duration to 400 microseconds, but this means that your RF power increases by 10-fold. So if you would run this type of pulses with a gradient echo sequence, there's no problem. But if you would run this together with BSSFP, you can forget about it because you run into SAR problems immediately. Another disadvantage of the pulse that we are applying frequency and phase modulation for fat suppression. So that makes it that the pulse is unselective. So you cannot use it to perform like slap selective excitation because you're using the properties of the pulse to excite already to be water specific. So, but how can we circumvent the SAR problem of the Libre pulse? There must be other ways we can do. So I went back and I was thinking, okay, but there are different flavors of water excitation pulses. We do not only have the conventional 180 pulse. There's also other flavors like the water excitation 1190 pulse. And the difference between these two pulses is simply that you do not wait for water and fat to dephase by 180 degrees. You wait for water and fat to dephase by 90 degrees, as you can see in the schematic. And then you apply a phase modulation of the second RF pulse. So by using this added phase modulation, you can make this pulse much shorter compared to the conventional on-resonance water excitation 180 pulse. So then I was thinking, can't we use, instead of increasing the RF excitation frequency of Libre to shorten the pulse duration, can we use an added phase modulation of the pulse to make the pulse shorter? So then we come to the Libre pulse, which is same but different. It's kind of a different flavor of the Libre pulse. However, we use phase modulation to optimize the RF power. And if you look at this type of graph where I represent the power increase as function of the pulse duration, you can see that with the Libre pulse, similar to the graph I showed before, we have a significant increase in the required RF power. With Libre, it's almost practically the same as a non-resonance water excitation pulse. So with the Libre pulse, theoretically, we can have fat suppression, but we don't have the SAR penalty. So these are the results in vivo. So just comparing all these different pulse of resonance pulse flavors, we have the Libre pulse, the Libre Bohr. I did not explain Bohr, but it's another flavor of resonance pulse, and another Libre pulse that is much longer. And you can see immediately that the fat suppression is the same in all pulses. However, if you look at the SAR deposit, this is more than 10 times lower compared to the conventional Bohr, not the conventional, but compared to the Bohr pulse. And it's almost more than 4 times lower compared to the original Libre pulse. So by applying a SAR optimized phase modulation, we can kind of reduce the SAR of the Libre pulse, which is very exciting. So now we have a power efficient pulse, we maintain fat suppression, and the benefit is also that because we are a bit less off resonance, we have decreased off resonance artifacts. And I don't know if you can see it on your screen, but you see this little halo here on the right. You see this kind of bright structure on the right of this knee, and this is less here. And this is really because of resonance. You get like this cloud-like pattern. And I think if you would do a Cartesian acquisition, you would have more artifacts that Thomas showed before. But because this is a radial acquisition, everything is a bit more smeared out. So, and especially this pulse could be ideal for Bees SFP at lower field strengths because we don't have so much SAR deposit and the pulses are very short. So just I finished this part about the water excitation pulses. Now I want to go a bit about our FIS work. So as Thomas already showed before, FIS is an interrupted version of a Bees SFP sequence. And in this case, I'm showing the sequence diagram of a Bees SFP sequence, where we have also phase modulated RF pulses that are phase cycled by 180 degrees. So you have minus 180, plus 180, blah, blah, blah. Oh no, sorry, it's not 180. It's the phase is 180, but the flip angle is of course around 60 degrees. If you look at the FIS diagram, it's interrupted. Thomas already showed before, a FIS module is you have the same phase cycling pattern in between RF pulses, but then you have another phase cycling pattern that is applied to the individual FIS modules. And in this case, we have an NR of 4 or N, where we apply an interruption every 4 readouts. So this is still a steady state sequence because you need it. And what happens is intuitively, you are changing the typical bending artifact observed with Bees SFP that you have here. You're changing it to a broader stop band, like a fat suppression band. And with this type of sequence, you obtain identical levels of SNR and contrast. If you look here at the magnetization as function of the RF excitation angle, you can see that at the on-resonance component of 0 Hertz, you have the same type of excitation. You have the same signal weighting T1 over T2. So this type of sequence would not need an additional T2 preparation. And you also have the same type of contrast. And we implemented this in a free running acquisition as follows. So we kind of divided this typical 3D spiral phyllotaxis pattern into 6 modules to have 4 readouts per interruption. And then we just acquire this continuously without any interruptions. And if you do this type of acquisition, Thomas explained this very well, like your repetition time and the amount of interruptions or the frequency of the interruptions really define the location and the width of the stop band. So in this case, I'm showing the pattern of 1 readout per FIS module. And in this case, I'm showing the pattern of 4 readouts per FIS module. And this first vertical line represents a fat frequency at 3 Tesla, and this one at 2 at 1.5 Tesla. You can see that if you do one readout per FIS module, where Thomas got very nice results, you have very nice fat suppression band here around the fat frequency at 3 Tesla and around here at 1.5 Tesla, but this sequence is quite lengthy. And if you look at 4 readouts per FIS module, you have also nice regions of fat suppression, but you're a bit more restricted in terms of TR choice. So especially if you go to lower field strengths, like 1.5 Tesla, the optimal TR is really below 3 milliseconds. And this is a problem if you want to perform high resolution scans, because if you increase your matrix size, your TR goes up, and then you will really lose some fat suppression capabilities. So we did some volunteer studies at 1.5 Tesla where we changed the resolution a little bit so that we were below the requirement of 3 milliseconds, and we used 8 readouts per FIS module. So in this case, you can see the comparison between FIS and BEAS-SFP. So these are motion resolved, these are free running. So this is a sequence where we implemented FIS in a free running framework. So we have cardiac motion resolved and respiratory motion resolved images. And comparing with the BEAS-SFP acquisition, you see that the fat is very well suppressed. And even the FIS acquisition doesn't suffer from this typical Indian ink artifact that you can see in the BEAS-SFP acquisition below. We also performed these studies at 3 Tesla, where your TR in a way is a bit less restricted because you can get away with TRs above 3 milliseconds. The optimal is actually 3.4 milliseconds, as we did here. Also, we used 8 readouts per FIS module, so you can get quite short scan protocols. And if you compare the FIS to the BEAS-SFP, we also see very good fat suppression. And also because the fat is better suppressed, we have reduction in the streaking artifacts that we observe. So just to quickly provide a summary of these two techniques, these several techniques, is that it's very hard to compare these methods one by one because there's really a field strength dependency. Because if you change the magnetic field strength, you will change a chemical shift. No, the chemical shift will be the same, but the frequency of water and fat, or the frequency difference between the two, will increase at higher field strength and decrease at lower field strength. So this will also affect the power requirement if you would use an off-resonance water excitation pulse like Libre and Bohr. However, it seems that with FIS, the lower the field strength, the better your fat suppression becomes, because you can really, your requirements for fat suppression are not the same as for the water excitation pulses. And it seems that with the Libre pulse, we kind of have the best of both worlds. So at the moment, we are running these comparison studies to evaluate them, but it's not a straightforward comparison because, I mean, you have also other artifacts that come into play. So I hope I've showed you some methods for water excitation approaches at different field strengths. Another very interesting development is that of water fat separation, but I do not have time for that now, but maybe for the next journal club when our paper is published. I would like to thank my colleagues very much, the current colleagues and the former colleagues, as well as several collaborators where we continue to develop Libre. And if you want to know more about FIS or Libre, there you can scan these QR codes that will take you to the references that I've talked about today. So thank you.
Thanks so much, Jess, for this nice overview of fat saturated sequences, and I like your QR codes here as well. Do we have questions from the audience?
I have a question.
Mariana.
Hi, Jess. Thank you so much for the talk.
You're welcome.
So I am interested in knowing a bit more about FIS. I'm actually curious about the way you integrate the different modules into the phylotaxis.
Yeah.
Because it kind of gives me the feeling that, you know, the first module will always kind of be in the more vertical part of the phylotaxis, and the last module will be more on the more horizontal part of the phylotaxis.
Yes.
You know, and do you alternate the modules, or do you do it always like this? And do you think that wouldn't cause a bit of uniformity in the K-space.
No, because you're in steady state. So once you are in steady state, your signal doesn't change. What you do is you have your phyllotaxis pattern. Say you have 24 segments, and you do 4 readouts per FIS module. So you divide your 24 segments into 6 FIS modules. This doesn't affect. If you look on the level of the K-space, your signal readout will be the same because there's nothing changed in the magnetization.
Okay.
So this shouldn't affect it. What affects it, how, if you say you have 24 segments and you want to use 3 FIS modules or 2 or 6 or 8, this makes a difference. And I think it's also what Thomas said. I didn't talk about RF spoiling and gradient spoiling, but this is super important, especially for if you want to reduce like flow artifacts, for example. Originally, FIS was not only designed for fat suppression, but also to reduce flow artifacts. But the way you reduce flow artifacts is really depending on the strength of your gradient spoilers. For example, and if you don't use a gradient spoilers, then that is like, it looks really rubbish. But if you make them longer, then you suppress the flow. They showed this in a paper of Edelman. However, if you do all these things, you change the duration of your gradient spoilers and you do 1 readout per FIS module, then you scan it's like 20 minutes. Like, it's not the solution really. So, but it's definitely things to be considered. And what I find personally very interesting is that the artifacts that I observe are so different from what Thomas observed. So it's really like, it's not only the FIS sequence, it's also like how you sample the K-space, right? There's certainly a trajectory dependency there. And this is something that, how do you even simulate that properly? It's super interesting. There's really something there. Maybe even like a Rosetta trajectory combined with FIS, to have something that's like double water selective, but that's too fancy.
Thanks, Mariana.
Thank you so much.
Sorry, I said many more things that were not related to your question.
No, it was good. I'm happy to hear it anyway.
You have a question as well from Chris Roy.
Hi. Can you hear me?
Yes, I can hear you.
Cool. Actually, just following up on Mariana's, that actually really does get me thinking, because I think her point was that the spoilers and the interruption, depending on your trajectory and your number of FIS modules, might sort of occur in the same location in K-space.
Yeah.
And we actually have, because we have done acquisitions with NR equals 1, and the image quality was kind of not very good, and we didn't really understand why. And I wonder if this is because the spoilers are always occurring in the same location of K-space. And then similarly, if you go to 2, you kind of have this, like you have the spoiling always occurring at the top of the sphere and at sort of the middle, and it's not dispersed throughout your spokes. So it'd be interesting to look at what the signal of those K-space lines actually looks like.
Yes, because if you go to 1 readout per FIS module, you also narrow your passband. So it also becomes a question of how off resonance are you in some regions of your tissue. Honestly, I don't really have the answer. I think it's rather complex, but definitely there's something else going on.
And then the other thought was, I really liked actually seeing Thomas's Cartesian images, because it's so much more clear what mixing, I guess, K-space lines that either have a little bit less or a little bit more fat suppression really does, because the ghosting artifact is so much more coherent. So even though we don't think we have that problem at Radial, we certainly have enough variable image quality, which makes me wonder if just because it's not coherent doesn't mean it's not there and doesn't mean it's not impacting, because there's certainly cases where I've seen kind of this, it's almost like there's a haze over the heart, and that would be very similar to what Thomas is seeing. It's just less coherent. So there's probably an optimization point somewhere where we lift this for a specific application or resolution.
But I also see it with Libre. If I change the RF excitation frequency, even in the knee, you get this halo that seems to be like shifted. So there's really something there that you have somehow some fall over of some off resonance excitation, which is the same for FIS actually. You have the same. And then I think with BSSFP, you would just have so much other artifacts that you don't even notice this halo. It's probably there, you just don't notice it. And then with FIS, you kind of suppress the fat, but then you see kind of these other problems that off resonance excitation brings. I mean,
it's always a trade-off.
I mean, excitation of resonance regions. I don't mean an off resonance excitation. Yeah, but there's certainly things to be done. But honestly, this takes so much time because you can't simulate this stuff anymore. No, you need to like live on the scanner and try all possible parameters. And it's like you're welcome.
Well, us other people that just want to reconstruct these nice images appreciate all the effort.
Definitely. I wonder how
Can I also?
do you think? Sorry. I just wanted to ask something else, but go ahead.
Ruud has been trying for half an hour to ask a question.
Oh, sorry, I didn't notice. My screen is so small. I actually don't.
I'm guessing I was the victim of that indeed, yeah. So can I jump in quickly? Sorry, Mariana, my arm was getting tired. So Jess, thanks for this great overview and a very nice presentation. I had a question about your Libor Pulse, which of course seems amazing. So there is no free lunch, right? So what is the not free part of your lunch? What do you sacrifice for Libor compared to Libre? Is it the bandwidth or what needs to go?
Yes, maybe a little bit.
Okay, so there's no, you don't have a clear sacrifice yet.
No, it's a little bit of bandwidth, fat suppression bandwidth.
Okay.
Yeah, but I guess you have to wait and see because it's work in progress. So.
Okay, thanks.
Thanks, guys. Any questions from Bordeaux? No, maybe one. Jess, if it's not too secret, can you tell us a little bit more about your new projects in Bern?
Yeah, sure. So my projects at this point are very much setting up the infrastructure of the lab. No, but to be sure, no, my extensive project is all about water fat resolved imaging. So it's mainly about the development of Spark, which is a project that it's about phase cycled BSSFP and using. So we are going to use phase cycled BSSFP to sample the BSSFP profile, and then we're going to use asymmetries you see in this profile to quantify fat and water. So this is a very efficient way, because not only will this result in fat resolved and water resolved images, but we have the initial paper on arXiv, but you can also use it to remove banding artifacts. So you can have a very neat images with high SNR plus quantitative. But then that's kind of the main part of the project, but then to kind of compare it, there's also FIS involved, because FIS is also a way of changing the an asymmetric profile. But also Libre, because Libre would be Libre developments would be used as a gold standard reference for fat suppression, and I think Libre works better at high field, so that's also part of it. But then it's like, I mean, it's a 5-year project with a lot of people, so it's a lot of different projects. But the main part is about water fat separation.
Right. Thanks, Thomas. Can I ask you exactly the same question?
Sure. So my job is to look at how can we translate all the different methods we have coming up in research more into the clinics. So I'm primarily also looking at artificial intelligence, deep learning based methods, ranging from the complete acquisition pipeline. So we're trying to look at from acquisition over reconstruction, post-processing to analysis. and bring all these methods closer to the doctor. So it's the right variety of not only MRI, different imaging modalities as well. But still a huge part is also still on sequence development in MRI for these kind of techniques.
Mm-hmm. So you might be interested in our next session actually, which is going to be a discussion on reconstruction framework with Valerie is going to talk about Gadgetron and David about FHIR. I don't have the date yet, but I'll forward you guys the flyer as soon as it is ready. Any other questions from Thomas and Jessica? No? So then let's thank...
Chris has his hand still raised.
Chris, you have?
Not intentionally.
All right. Thanks again, Thomas. Thanks again, Jessica, for your time. Matthias has a question. All right, Matthias, go for it.
I don't have a question. I would like to really thank you, Aurélien, for organizing this journal club, being persistent, relentlessly hounding us to participate. I think it has been a great success. There were so many interesting presentations. Big thank you to you and happy holidays also to Porto and to everybody who is on the call.
Thanks, Matthias. I promise you a very nice session for next year with great speakers. So same here. I wish you all a lovely Christmas and see you next year. Bye-bye.
Bye.
Okay, bye.
Bye.
Bye-bye.